Akkor én tisztelettel köszöntenék mindenkit. Szabó Áron vagyok, az E-Groupnál dolgozom. És most ebben a következő 40-45 percben a kriptográfiához kapcsolódó közeli jövőről, illetve ennek a közeli jövőnek a jelenre való kihatásáról lenne szó. Tehát, hogyha valaki most mondjuk ilyen jellegű rendszereket szeretne tervezni és fejleszteni, akkor mikre kell már mondom a jelenben is figyelni. Az előadásban utána szó lesz, hogy kicsit a konkrétumokba is belemenjünk egy hash-alapú aláíró algoritmusról is. Most ennek kapcsán nyilván nem tudom elkerülni azt, hogy valamennyire a matematikai hátteret, illetve egy ilyen konkrét algoritmusnak a működési logikáját megnézzük, de hát mivel én sem vagyok fizikus, meg matematikus, ezért megpróbáltam emészthető módon ezeket leírni a szlájdokra. Jó, hát ugye azt tapasztaltuk itt az elmúlt időszakban, hogy fejlesztőként kriptográfiától
I'll talk about issues that you need to pay attention to if you are developing security-related apps. I'll also talk about the mathematical background a bit. Here in the post-kvantumkriptography algorithms, you shouldn't forget that in the past 10 years we have seen a lot happening in classical cryptography. You shouldn't forget the MD5 collision published about by Professor Levent, and the first countermeasures only happened in 2012, and they were induced by the appearance of flame, which utilized MD5 collisions to generate a Microsoft key and certificate, which could then be used. This code signing certificate could then be used to sign modified Windows updates. Microsoft immediately proceeded to delete MD5 signed updates from its stores. You shouldn't forget what happened in the standardization institutes about the parameterization prescribed for random number generation. This is the topic of kleptography, which you could hear about today by another presenter. And we should not forget about the fact that it is very easy to downgrade algorithms simply by decreasing the entropy of their random number generators. Just think about the fact that in 2006 there was a modification in the OpenSSL which affected its random number generator, and it only became public knowledge 2 years later, 1.5 years later. But to not go back so deep in time, even a year ago, Android was found to have a similar vulnerability, and in a situation where a good quality random number generation is of the essence. Also, we need to be aware how these algorithms should be used, and its textbook example for this was provided by the failover group using a Sony PlayStation, where the group used the LCD algorithm for signing, but the developers due to developer problems or the background libraries returning a bad value, the returned random number was not a real random number, so they could actually break it. I could also mention here the SSL web service settings, where the question is what is worse. We either ensure a good quality random number generation and introduce Diffie-Hellman key-based checking, or if we doubt this, then we set an RSE-based key replacement. But that's but in this case, if the web server itself is compromised and the key is accessed, then all the traffic will can then be reverse engineered. We also shouldn't forget how important code audits are. We have seen good examples for that today. Increasingly, either the 4 levels of common criteria are required for code developers. So independent third parties validate code based on that. The latest such audit was made on TrueCrypt last year. We heard that there are no severe problems with TrueCrypt, but it's not a simple story because it may take years until a really audited code can be marketed, because it takes that long to validate it. Getting back to code audit and open source solutions, let me get back to the problems of OpenShell. OpenShell is open source. We use it. It's easy. It has a command line interface as well. It can be used to a lot of things. But we mistakenly often believe that somebody else has certainly audited this at source code level, but the opposite was proved by the random number generation problem that was in the code for 1.5 years. And you also remember the heartbeat story. That vulnerability was in the source code for 2 years. Another thing I thought about is something that is related to the Edward Snowden story. Various companies came up with various solutions. There are problems here, our solutions, use this and we'll encrypt. NSA cannot listen, cannot decrypt it, so it's great. But if you looked at these applications, we often saw that they were still calling the same Microsoft API or the same OpenSSL library or Java X-secret class or whatever, or they use the same browser implementation. So in reality, everybody built on the same faulty foundations that they intended to solve the problem with. We also see new things appearing. These various cryptographical algorithms, based on their behavior, are also different from classical, are different between classical and quantum computers. We see that there are companies that advertise themselves as having some sort of quantum architecture computer that it is marketing. We also see or read that it's probably not able to run a single line of code. But we also see that Lockheed Martin, since 2011, has been closely cooperating with the company, so we still do not know what the real situation is. But we see one thing: we need to learn about this, and we need to know what to prepare for, but we can say nothing that we can be sure of, whether quantum computers exist, and if they don't, when they will exist, realistically. If there will be quantum computer, the portal of pqcrypto.org published a very good description. RSA is dead, DSA is dead, elliptic curves are dead, Diffie-Hellman algorithm is dead. So what do we have instead? Hash-based algorithms will still work. Cleanly symmetric cryptography will still work. And there are other mathematical problems which you can base algorithms on that will work. Why do they say that the current crypto algorithms are dead? This affects primarily Shor's algorithm used for prime factorization and perform it in polynomial time. And also the Glover algorithm is mentioned in this respect. Okay, these things exist, but what do we do with them? If you think about it, we can say that my signed data, are not really in danger. The integrity of these data is not really in danger. Up until the last second, we can put a new layer around them, a signed layer that we can use to further protect the data. And we can present a signed data set of data that can then be checked and controlled even in the quantum era. But the encryption causes a problem. I don't know how many of you have put up encrypted data for challenge even, visible to the general public, but we must know that in the post-quantum era, only cleanly, absolutely symmetrical crypto will be the only thing that will also be considered safe on a quantum computer. In most cases, however, just look at, for instance, office documents or BGP operation, pqc's, crypto message syntax, S-MIME, whatever. If you look at these data structures, you see that they use something similar to SSL handshake, but they use cryptography in a hybrid manner. What does that mean? It means that encryption uses a symmetric key, for instance, an AES key, but this symmetric key is sent using asymmetric cryptography through the channel or deposited in a similar or encryption file. So if you store one of these and wait for a couple of years, and then you will buy a quantum computer, then can feed the stored value into your quantum computer. An RSA-protected AES key can then be decrypted, and then using this you can decrypt the encrypted data. I have written a concept here concerning SSL server settings. There is a perfect forward secrecy. This concept is about the fact that if the web server is compromised, so when the RSA secret key becomes public knowledge, then what happens? Then the data traffic can then be decrypted to make it more difficult for black hats to decrypt it, to make it a Diffie-Hellman-based key matching is recommended, where the client side, the user browser, also generates secret data which protect against this simple attack. In the post-quantum era, this may have to be rethought and maybe extended, because we need a quantum-safe, perfect forward secrecy, which would tell us what algorithms were used to store these data and whether these algorithms will be good in the quantum era or not. So we'll need to think about this already today, especially if you want to publish encrypted, sensitive data, and you want to make it protected not only for 10 years, but also for 90 years, because it's a national security-related issue. I mentioned the Shor algorithm, and very simply a little maths now. The Shor algorithm, or the modified Shor algorithm, is able, in a quantum environment, to utilize some superpositions and parallelisms to perform certain things, not in exponential but in polynomial time. The things relate to searches. The Shor algorithm consists of two parts. Part one finds the period term of a function, and the second part finds the largest common divider. Let's take a look at the maths. We have an RSA modulus are equal to 15. Let's say this is the modulus. We'd like to factorize this. We need to select a random number smaller than this modulus. Let's make it 7. And if a on the power of x n, we must check this function's periodicity. We see the remaining values after the equal sign, and we see that the period starts repeating after the 5th step. So the periodicity of this function is 4. Then you take the Euclidean algorithm, and you see the function that we need to to check for their largest common divider. This is 48 and 15 for case 1, and 50 and 15 respectively for case 2. If you check the deduction, you see that we actually do receive p equal to 3 and q equal to 5, which are the 2 prime factors of 15. So this is the algorithm that will run a lot faster in a quantum environment. So this is why the RSA algorithm is dangerous if once quantum computers will be available. As regards the Grover algorithm, I show here a table from the documentation of the ETSI work group dealing with this issue. The essence is that using symmetrical cryptographical algorithms, we must be aware that in quantum environments, the strength of these algorithms will be roughly halved. So as while in traditional computers, the level was 2 on the power of 32, and now this will be increased to roughly 128 in the quantum era. Now that we see what the reasons are for our worries, let's have a look at what we can choose then in the future. The Post-kvantumkriptográfia has a good summary, and other documentations also show that there are mathematical problems and algorithms based on them that will still be functioning in the post-quantum era. Unidirection functions are one example, hash-based algorithms. This is what we'll have a look at in a couple of minutes. Lamp board is also still a good algorithm, but they do have a disadvantage. One is that you can only use them with a signature, so you can't use them for encryption. The other drawback is that you cannot use them any arbitrary number of times, once or up to a number of occasions of n. The grid-based, the lattice-based solutions will also throw up Hungarian names like Ajta Miklós, Miklós Adai and László Lovász. The good news is that here you can use encryption and signatures. You have shortest and closest vector problems as the basis of the algorithm. The N2 algorithm is patent protected, so it's a bit more difficult to use. There are also other mathematical problems like multivariate equations-based problems. They can only be primarily used for creating signatures. Also, there are code-based algorithms. Error correcting codes. These will probably be preferred. The McAlice or the Niederreiter algorithm can be used both for signatures and for encryption. And don't forget that symmetric cryptography will be still workable. These mathematical problems and the algorithms that are based on them can be found in scientific publications, but they are not easily accessible to a developer as yet. So for us, what is important is to have them embodied in some sort of a technical standard, and we have a look at what standards are already available in the field. Actually, the standardization work, whether Edward Snowden has something to do with it or not, shows that it started around 2013-14. In 2005, there was a standardization attempted and true, but it died. Then in 2014, several IETF and RFC drafts appeared that primarily dealt with hash-based signature algorithms. They specified these algorithms. And I picked one of these. And what I'd like to mention is that ETSI, the European standardization body, also set up a quantum cryptography work group, although they primarily only issued a sort of guideline. They did not specify any algorithms as yet. And what needs also to be mentioned is, while we are talking about guidelines, is Daniel J. Bernstein and his team, who on the one hand, they submitted an algorithm specification, and at EU level, they are about to issue all sorts of recommendations for developers. This is a relatively new documentation. If you look at it, it's totally current. It was published on the 7th of September this year.
As I have mentioned, I actually selected hash-based algorithms, and there's a reason for that. Beyond RFCs being born for them, and I haven't actually emphasized that, but hash-based algorithms have a huge advantage. They are very simple. We know the saying, keep it simple, stupid, which plainly means that we have a less opportunity for errors. If in a hash-based algorithm, if the hash is okay, then we can't have a great problem. In other cases, we have other complicated calculations to be performed. But it turns out that the reason why this became sensitive was not hashing itself. If something is simple, it might actually be good in cryptography. Let us now specifically examine the LDWM, Lamport-Diffie-Wenten-Markov algorithm. It was perhaps it was surely an important aspect in the selection that there are test vectors in the draft, therefore the quality of the code was easy to examine. I could easily validate the code, in other words. What do we require in order to use such an algorithm for a signature? We're going to use a hash-based signature algorithm. First of all, we have to select a group of parameters, which we have to provide instantly at the key generation. In this example, SH25060, and we have a 1. We'll see what that means. If we go along the parameters, the names are the same as in the RFC, so it's very easy to pair them. H and F are about two hash values. SH256. What we see here, LDVM types, LDWM type signatures are comprised of a set length. For this, you have to know an LDWM signature is made up of a p number of n length pieces. That suffices for the time being. N parameter provides the length. W is taken out from a set character, from predefined character set. SKMS probably uses this parameter, so it's quite useful. With the different value sets, however. In this case, it got a value of 1. But what's the main essence here? The winter-midth parameter, the W parameter, is about how we want to play about with the cost of the CPU and the cost of the storage. We have a smaller amount of hash iteration in winter-midth, but the keys, that is the signature value, takes up a larger storage in the case of a smaller one. If in the case of a larger winter-midth parameter, there are more iterations, so it has a higher CPU demand. The USB parameter and the length, they're just basically check figures, and to that we add these also count into the P parameter, where I said that the P was none other than the number of the M-length data which are featured in the LDWM signature, and not only there but also in the encrypted key. So these are the parameters. Let us now look at the process. If someone wants to use such an algorithm, so if you want to sign something, then what do you have to do? As a first step, we generate an encrypted private key. In the case of a private key, as I've mentioned, we have a P number n length data, where n comes from the impression function, so I have to come up with random numbers, and I have to apply the SH256 algorithm. In this example, if we add the check number, we have 265 such hashes, and this constitutes the private key. I also wrote down for myself something I must not forget, and I already mentioned it, namely that this algorithm is also made in a way that you can only use the private keys once. So after the key has been generated, the private key, and we have applied it for providing a signature for red data, then we have to make sure that it is deleted in a safe manner, because we must not use it as a signature for a different set of data, because in some cases that would make it easy to deduce the secret or private key. So these are one-time keys. They can only be used once. These private key pieces, or the sets of parameters, have to be brought together, which is provided by the RFC, but is not featured in the scientific documentation. X509 and similar data structure will be what I shall use to present the operation of this algorithm. So I actually came up with a very similar structure. If you have seen different or similar keys at a binary level, you can't really see anything different, because you know with the P and the Q, the D and E in the case of a private key. The only difference here is that the first element is a parameter identifier, LDWM M36 Winternets 1. Yes, this has one code, and this is followed by the hash. We have the private key. Let's generate the public key. The generation of the public key
mértékben végrehajtott hashelés.
Is hashing determined by the Wintermans parameter. If the Wintermans parameter were 8, then we should hash every single key piece 255 times in order to come up with the public key pieces. I was actually thinking, this has a higher CPU demand, but if we think of that today in general, any password check has a figure of 5,000 in iterations. This isn't even all that high a figure. Never mind. The main essence here is that the key pieces will become hashed private key pieces, but that is not the private key pieces will be hashed public key pieces. This is not the public key, however, these have to be stringed together, and the end result will be a single hash and the set of parameters. If we look at this at this level, this is what it means.
Van akkor egy nyilvános kulcsunk,
So we have a public key.
És hát nézzük meg, hogy ezt mondjuk egy hitelesítés szolgáltató, tehát egy CA,
Let's us see how a certificate authority can actually place that into a certificate.
Igazából majdnem minden itt is már megvan.
We practically have everything available here. If you look at the parts under the parts highlighted in blue, you have the parameter set ID and the hash, which is a public key. But apart from that, we require another identifier, which is an object identifier, an ODI. You have ODI in any RFCs, but haven't seen it yet, so I actually borrowed one from the Darmstadt University, which is a one-time usage, single-use Lamport type. Which can be used for one-time usage, Lamport type signature algorithms, and after I have made this algorithm set, you have to sign it that this is a real certificate, except for 509 certificates, and if we look at in the Windows operational system, then we see well, what we see here on the central parts of the image is that this OID is an unknown OID for Windows. It does not know what data structure it has, but until this implementation isn't ready, these can be managed with a separate application, and in a quantum safe mode you can create signatures. We have the private key and the certificate with the public key, and we'd like to select the data to be signed. Nothing extraordinary here. The data to be signed can be anything. We have to read it in a binary way. Let's now create the signature. We have the data, we have the private key, and something similar happens here as in the case of generating a public key. We have to send these private key pieces through hash creation, but not as many times as in the case of the public key hashing. How many times, as for how many times we have to iterate this, that depends on the bits of the data to be signed, and this is where the connection is made between the data to be signed and the signature created with the private key. In the case of a Wintermits 1, this isn't very spectacular, but for a Wintermits 8, we have to iterate 255 times for the public key, and in the case of a signature, maybe only 67 times. This is what will be incorporated into the signature value. All I have to add to this is that there is a check number value which also has to be concatenated to the impression of the data, and this private key is, the hashing of private key is executed there too. And the signature structure looks the same as in the case of the private key structure, but now we have the hashed key chunks or parts. You have to provide the identifier of the set of parameters, and you have to see the P number as well. The 265 impressions which was calculated from the private key, depending on the data to be signed. This is the interesting part. How can we validate this? How can we verify it? In the case of a quantum it's equal 8, we have to hash 255 times, but in this case we hash 67 times. The question is, how many times do we have to hash the data chunk in order to receive the public key that is featured in the certificate? We can know that depending on the signature and the signed data. So we have to continue hashing as many times the public key was hashed during the creation of that key. If we are successful, the iteration figures were correct that were calculated from the signed data and were executed on the signature chunks, then the signature verification program will see a match between the key and the impression. And that's all there is to it, basically. In this current code, we use the WinTimid 1, so this was a single iteration. And it's perhaps not so spectacular, but in the case of a WinTimid 8, you'd see it better, perhaps. This is actually a change as compared to RFC. How did we verify signatures there? We actually coded back through the public key the signature value, and then we ran a hash creation on the signed data. And here practically we have to compare the public keys, so the story is somewhat different. And this was the operation of the LDWM algorithm, and now let's summarize the positive and negative aspects. So let's recap what I've mentioned so far. During the application of a hash-based algorithm, we have to pay attention to, there's a general rule, that we have a very good random number generator, that we have to have a good quality figure before it's a number, and we shouldn't have little loopholes, as we saw in the case of Norbert. The other important aspect is that this can only be used once. LDWM can only be used once. There are other algorithms where there's an opportunity for multiple use of the keys, and you can build Merkle trees out of it, but that would be that would require a more serious key management. This is a fixed single-use algorithm, and this does not only go for the end-user key, but if we establish a CA, we create 10,000 keys, that would be one single signature that we signed once, and then we have to delete the key of the CE as well. On the other hand, we must not forget this, there is no other mathematics in the background, just these simple functions, and the usage is very easy, it's simple and secure, it's simple to use actually. If we do not introduce a Merkle tree, it can only be used once. And what's most important is that just the fact that it's a single use, it cannot be used in the case of a web server, but It's absolutely great for human usage, like in the case of e-voting systems or public administration. And that's all I wish to share with you, and as far as I can tell, my time is up too. There is a code for the screenshots I have shown you, and you can download them from the address you can read here. Thank you very much for your kind attention.